All right, for this first problem, it says use a graphing utility to graph the function and visually estimate the limits. So we want the limit as x approaches 4, which is right here, of h of x. So it looks to me like the limit from the left and the right is coming out to 0. And the limit as x approaches negative 1. Oh, I just realized that's negative 1. I think the key that I posted, I did 1 instead of negative 1. So, okay, negative 1 is not on my graph. We learned about direct substitution today, though. So I am going to say that I can just plug in negative 1 here. So that's going to equal negative 1 squared is 1, and then plus 4 times negative 1 is minus 4. So that should be negative 5. Remember, negative x squared is always negative. You square the number, and then you multiply by negative 1. Okay, so that answer is negative 5, not 3, like I had before. I'll fix that. Okay, number 6, we're just taking a limit. So again, direct substitution, that's all you're doing here. Negative 2 to the 4th is 16. The limit as x approaches 4 of the cube root of x plus 4 becomes the cube root of 4 plus 4. And then that simplifies to 2. Now we have f of x and g of x. So find the limit as x approaches 1 of f of x. So just make sure you're plugging into the correct function. So this is just 4 minus 1, which is 3. The limit as x approaches 3 of g of x. This line doesn't mean anything. That is the square root of 3 plus 1. So square root of 4 is 2. And then the limit as x approaches 1 of g of f of x. Now, I'm not going to find g of f of x. I could plug f into g, I suppose. But I could also just say that's equal to, direct substitution still works here, g of f of 1. F of 1 is equal to 3. So now this is g of 3. And g of 3 is equal to square root of 4, which is 2. But if you found g of f of x, you could say that's the square root of 4 minus x squared plus 1, square root of 5 minus x squared. And then if I plug 1 into that, I get the square root of 5 minus 1. Square root of 4 is still 2. So you could still get the same answer doing that. I just, if I can compose and plug numbers in right away, I think that's faster. All right, then we're finding some limits for the next section. So direct substitution, what's the sine of pi over 2? Remember, sine around the unit circle is the y value around the unit circle. We're at the top of the circle here, so that's 1. What about cosine? This is cosine of pi over 3, pi times 1 over 3. So remember your ordered pairs. Pi over 6 is down here. Pi over 3 is up here. So which is which? I kind of have memorized that the sine of pi over 6 is 1/2. So I kind of, in my brain, go around this way. But whatever. You still need to know these two ordered pairs, and you need to have them straight. Okay, so the x coordinate at pi over 3 is 1/2. For 32, the cosine of 3 pi. Okay, now remember, 2 pi is a full circle. Here's 2 pi. 3 pi, or any odd multiple of pi, is going to be the same as pi. So what's the cosine of pi? Cosine of 3 pi, it's equal to negative 1. All right, now this next section I realize is kind of, we will talk about these properties tomorrow in our notes officially, but they are pretty, like, if you had to guess what to do, it's what you would guess, I would hope. So if you have a constant in front of a function and you're taking the limit, it's still just that constant times the limit as x approaches c of g of x. So that limit is 2. This is 5 times 2, which is 10. If you're adding two functions inside of a limit, you can say that's the limit of f plus the limit of g. Same thing with multiplication. 3 times 2 is 6. And same thing with division. This becomes 3 divided by 2. All right, so that's not bad. And then Next one, we've got the limit as x approaches c of f of x is 27. So the first one is, what's the cube root of 27? That's 3. This one is 27 over 18. Reduce that by 9, so that's 3 over 2. (27 squared). Honestly, we can leave things like this for our AP test, although 27 squared, we ought to be able to do a little math here, dust off the pencil and paper math. So let's see, 14 plus 4 is 18, placeholder, 14, 5, boom, 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 729. Or you could do it this way, 20 plus 7 squared is 20 squared plus 2 times 20 times 7 plus 7 squared. I'd still be adding up a bunch of numbers. 400 plus 49 plus, what is this, 280? 40 times 7? Yeah. Anyway, it's 729. What about this one? This is 27 to the 2/3, which means cube root of 27, that answer squared. Cube root of 27 is 3, that answer squared is 9. All right, use the graph to determine the limit visually if it exists. Write a simpler function that agrees with the given function at all but one point. So that sounds kind of complicated. All this is saying is you can see this graph. This is a rational expression, but it looks like a parabola with a hole in it. And that's just because we must be able to simplify g of x. So if I work on g of x a little bit, if I factor out an x, which leaves me with an x minus 1 that can, factor out an x and you're, there we go. Factor out an x and you're left with x squared. There we go. Minus 1. And then that can factor a little bit more. I knew something was wrong because I was getting like a line instead of a parabola. So I factored out an x. I factored the difference of squares. The x minus 1s could cancel. So this is why g of x looks quadratic with a hole in it. Because you get x squared plus x where x can't equal 1. So that's still g of x. So all they mean by write a simpler function that agrees with the given function at all but one point, if I just say, okay, f of x is just x squared plus x, no restriction, that would be the same parabola and it would fill in the hole right there. So you don't have to get crazy. That basically just means, hey, simplify g of x and call it something else. I chose f of x. Okay, and then we can still just use this graph to find these limits. Or we could use direct substitution on the simplified function. So the limit as x approaches 1, then, is the intended height of the function, which is 2, even though there's a hole right there. And the limit as x approaches -1, again, the intended height of the function. This does not have a hole. That's equal to 0. We could verify that. If we plug in 1, we get 2. If we plug in -1, we get 0 into our simplified function. A few more limits with rationals. So I can't plug in 4 right off the bat. I get 0 over 0, which is an indeterminate form. But I can simplify this. Now remember, if you simplify this, I'm going to get kind of lazy and write my work under here. It would be wrong for me to say this limit, it would be wrong for me just to say it equals 1 over x plus 4 and that equals 1 over 8. That's wrong. Wrong. Because you don't have the limit notation here. So remember, you need to keep your limit as x approaches 4 of x plus 4. And then once you do direct substitution, then you're allowed to drop limit notation and just get your answer. All right, same thing here. Let's just factor up here. So this trinomial factors into x plus 3 and x minus 2. This is x plus 3, x minus 3. So x plus 3's divide out to 1. So now it's the limit as x approaches -3 of x minus 2 over x minus 3. And when you plug -3 into that, I get -5 on top, -6 in the denominator, so positive 5 over 6 is my overall answer. All right, now 55 and 60, I wrote this on the board. We're actually going to cover this process in our notes tomorrow. I will still explain this because we did this kind of simplifying in pre-calculus last year, and you might have done it in algebra 2 as well. So again, direct substitution fails because if I plug in 4 right now, I get 3 minus 3 on top, and I get 4 minus 4 on the bottom. So how can you work on this? We can do something called multiply by the conjugate of the numerator in this case. So all that is keeping the same binomial but changing the sign in the middle. And you're allowed to do that on the top and the bottom as long as you're doing both, because all I've really done is multiply by 1. So I'm not changing the value of anything. I'm just multiplying by an expression that will help me in the end. So, all right, so how does it help? So let's look at what we get when we multiply the conjugates together. We should remember when we multiply conjugates, we just have to multiply the first term and the last term together because the inside-outside parts cancel. So radical x plus 5 times itself is x plus 5. Negative 3 times 3 is minus 9. We don't multiply through the denominator, so let's leave x minus 4, got to put it in parentheses, multiplied by parentheses square root of x plus 5 plus 3. Now this expression in the numerator, this is x minus 4. So this can cancel with this. So now it's the limit as x approaches 4 of 1 over just square root of x plus 5 plus 3. Okay, so what have I done? Well, it kind of looks like I just got the radical out of the numerator and got it in the denominator, but try a direct substitution again. And if you plug in 4, you don't get a 0 over 0 outcome. You get the square root of 1 over the square root of 9, which is 3, plus the other 3. So you get 1/6. All right. A similar idea for number 60. If I plug in 0 right now, I get 1/4 minus 1/4 over 0. 0 divided by 0 is called an indeterminate form. It means we've got to work on this more to see what the real limit is. And we simplified complex fractions like these in pre-calc. So remember, there were 2 ways to do it. You can do the math common denominator in the top and then rewrite the division problem, or my kind of streamlined way to do it was to say multiply by the least common denominator, so 4 times x plus 4, multiply by that least common denominator in the top and the bottom again, because again, you're just multiplying by 1, so this is legal that we're allowed to do this, and then we distribute this to each term, and so we get the limit as x approaches 0. So the x plus 4s are going to cancel. You'll be left with 4. Minus, now the 4s are going to cancel. You'll be left with minus parentheses x plus 4. There is no fraction in the bottom. It's just an x. So this just gets multiplied together, but not distributed. I'm just going to, instead of x4, I'm going to write 4x. Leave this x plus 4 out here. The reason I don't distribute it is because when we simplify the numerator, write out my limit notation. When we simplify the numerator, we're going to get 4 minus x minus 4. So we're just going to have negative x up there. Still have 4x out here times x plus 4. So keeping this 4x factored out shows me that I can divide that x with that x, and they divide out to negative 1. So when I plug 0 into here, I've got negative 1 in the numerator, 4 times 0 plus 4. So the limit is negative 1/16. All right, so again, we will do this again in the notes, and then you'll have it again in homework number 3. All right, this says, in this exercise, use a graphing utility to graph the function and estimate the limit. Now, you would just be estimating the limit if you're just going with a graph. And at the time, my calculator wasn't working, so I used Desmos, but I want to do this in a calculator. Oops, not that one. Sorry. I want to do this in a calculator to show you a couple of tricks. I think I showed this in class today, but I can't remember. So I want to type this function into y equals. Sorry, I want to type this function into y equals. You can use parentheses like they have here, or we do have, I didn't really realize this until sometime last year. If you press alpha y equals, this little n over d gives you sort of like a math type fraction. And then I think I can do it again. Let's see. Yeah, okay, I can do it again here. So what were we trying to type in? We were trying to get, let me split this here. We were trying to get 1 over 2 plus x. So now that, see how it's doing that like math type, so that's kind of nice. And then minus, again, I can say 1, oops. I didn't have to use the fraction there. I could probably just say, minus 1 divided by 2. I just wanted to keep it looking nice. And then it's over x. All right, so we want to graph this. Our limit is near 0, so our graph just needs to include 0. So I'm just going to zoom 6. And then I can kind of trace to get this close to 0. I can also do second trace and like put in a value that's very close to 0, but not quite, like something like this. And see how it's telling me, like, yeah, it's just negative 1/4. So if you let yourself get close enough, maybe with second trace and plugging in a value, try it on the negative side. Oops. We'll try it on the negative side too. Something pretty close to 0. Yeah, it's just going to default to saying, oh, negative 1/4. So when I estimate it on the graph, if I'm just looking at this, I might say like, I don't know, negative 1/2 if I'm just looking at that. But if I get a little closer in my graphing calculator, it looks like negative 1/4. And I can verify that accurately. So it says use the table to reinforce your conclusion. Okay, I did that sort of with my value on my calculator, and then find the limit by analytic methods. So that just means let's go ahead and do the math on the limit. So let's do that trick with getting rid of the complex fraction. So we're going to do that by multiplying by 2 times x plus 2. And that becomes the limit as x approaches 0. So the x plus 2's cancel, 2, minus the 2's cancel, quantity x plus 2, over 2 times x plus 2. All right, now remember here the negative distributes through, so you're really just left with negative x up there, and that x is going to cancel with that x. So sorry, that was a pretty ugly way to cancel all of that, so let me clean this up. I have just negative 1 on top. I have 2 times x plus 2 down here, and that is negative 1/4. All right. Oh, and that was the last problem. All right, come into office hours if you're having questions on any of these or if you want some more practice.